Scottish D does manufacture 40 and 50 amp HOM series circuit breakers, but they are not available as double pole quad breakers. The maximum amperage available for a double pole HOM circuit breaker is 30 amps. If a 40 or 50 amp double pole quad circuit breaker is required, a different approach will need to be used. Here are a few alternatives. Firstly, use two separate 20 or 25 amp double pole HOM circuit breakers. This will provide the same amperage capacity as a 40 or 50 amp breaker, but will require more space in the electrical panel. Secondly, use a different type of double pole quad circuit breaker. Other manufacturers, such as Siemens or GE, may offer 40 or 50 amp double pole quad circuit breakers. However, verify compatibility with the existing electrical panel. Thirdly, install a subpanel with its own circuit breakers. This is a more complex and expensive solution, but it will allow for the exact amperage and configuration of circuit breakers needed. It is generally not recommended to try and use a non-standard circuit breaker in the electrical panel. Doing so could create a safety hazard. If it is unable to find a 40 or 50 amp double pole quad HOM circuit breaker, it is best to consult with a qualified electrician to determine the best alternative solution for the application. When selecting a circuit breaker, there are several important electrical characteristics to consider. These characteristics ensure the breaker will protect the circuit and equipment from overcurrents and short circuits. Firstly, amperage rating. The amperage rating is the maximum amount of current the breaker can carry continuously without tripping. It must be matched to the circuit's wiring and the load it will serve. Using a breaker with a lower amperage rating than the circuit requires will result in nuisance tripping, while using a breaker with a higher amperage rating can allow the circuit to be overloaded, potentially causing a fire. Secondly, voltage rating. The voltage rating specifies the maximum voltage the breaker can safely interrupt. It must be equal to or greater than the voltage of the circuit it protects. For example, a 120/240 volt breaker can be used in a 120 volt or 240 volt circuit, but a 120 volt breaker cannot be used in a 240 volt circuit. Thirdly, interrupting capacity. The interrupting capacity, also known as the short circuit current rating or SCCR, is the maximum amount of fault current the breaker can safely interrupt without being damaged or causing an arc flash. It is measured in amps. The interrupting capacity must be greater than the available fault current at the breaker's location. If the available fault current exceeds the breaker's interrupting capacity, the breaker can fail catastrophically during a short circuit. Fourthly, pole configuration. Circuit breakers are available in single pole, double pole, and 3-pole configurations. Single pole breakers protect a single 120 volt circuit. Double pole breakers protect a 240 volt circuit or two separate 120 volt circuits. 3-pole breakers protect a 3-phase circuit. The pole configuration must match the circuit's wiring. Fifthly, trip curve. The trip curve describes the breaker's response time to different levels of overcurrent. Different types of trip curves are available for different applications. For example, a Type B breaker trips quickly for small overloads, while a Type C breaker trips more slowly for small overloads but quickly for large overloads. The trip curve must be selected to protect the specific equipment being served. Sixthly, agency approvals. Circuit breakers should be listed by a recognized testing laboratory such as Underwriters Laboratories or UL. This listing indicates that the breaker has been tested and meets safety standards. Using a non-listed breaker can create a safety hazard. In addition to these electrical characteristics, there are also some mechanical characteristics to consider when selecting a circuit breaker. These characteristics include the breaker's physical size and shape, its mounting method, and its terminal type. The breaker must be compatible with the electrical panel or enclosure in which it will be installed. Furthermore, the terminal type must be compatible with the wiring being used. When selecting a circuit breaker, it is important to consider all of these electrical and mechanical characteristics. Selecting the wrong breaker can create a safety hazard or prevent the circuit from operating properly. If there are any questions about selecting the right circuit breaker, consult with a qualified electrician. To further elaborate on circuit breaker alternatives, firstly consider using multiple single-pole breakers instead of a double-pole breaker. If the application allows, 2 single-pole breakers can be used to protect 2 separate 120-volt circuits. This can be a cost-effective alternative to a double-pole breaker, especially if space is not a concern. Secondly, consider using a tandem breaker. A tandem breaker, also known as a twin breaker or a half-size breaker, is a type of breaker that allows 2 circuits to be protected in the space of a single breaker. This can be a good option if space is limited in the electrical panel. However, it is important to make sure that the electrical panel is rated to accept tandem breakers. Thirdly, consider using a ground fault circuit interrupter, or GFCI, breaker. A GFCI breaker protects against ground faults, which can cause electrical shocks. GFCI breakers are required in certain locations, such as bathrooms and kitchens. A GFCI breaker can be used in place of a standard breaker to provide additional protection. Fourthly, consider using an arc fault circuit interrupter, or RFSI breaker. An RFSI breaker protects against arc faults, which can cause fires. RFSI breakers are required in certain locations, such as bedrooms. An RFSI breaker can be used in place of a standard breaker to provide additional protection. Fifthly, consider using a surge protector breaker. A surge protector breaker protects against voltage surges, which can damage electronic equipment. Surge protector breakers are available in both single-pole and double-pole configurations. Sixthly, consider using a shunt trip breaker. A shunt trip breaker can be tripped remotely by an external signal. This can be useful in applications where it is necessary to be able to de-energize a circuit from a remote location. Seventhly, consider using a low-voltage breaker. A low-voltage breaker is designed for use in low-voltage circuits, such as those found in industrial control systems. Low-voltage breakers are available in a variety of amperage and voltage ratings. Eighthly, consider using a molded case circuit breaker. A molded case circuit breaker is a type of breaker that is commonly used in commercial and industrial applications. Molded case circuit breakers are available in a wide range of amperage and voltage ratings. Ninthly, consider using an insulated case circuit breaker. An insulated case circuit breaker is a type of breaker that is designed for use in high current applications. Insulated case circuit breakers are available in a variety of amperage and voltage ratings. Tenthly, consider using a solid-state circuit breaker. A solid-state circuit breaker is a type of breaker that uses solid-state components to interrupt the circuit. Solid-state circuit breakers are more reliable and faster acting than traditional electromechanical breakers. When selecting a circuit breaker, it is important to consider all of the factors discussed above. By carefully considering these factors, a person can select the right circuit breaker for the application. Now let's discuss some common issues that might arise when dealing with circuit breakers. One common issue is nuisance tripping. Nuisance tripping occurs when a breaker trips for no apparent reason. This can be caused by a number of factors, such as a loose connection, a faulty appliance, or a voltage surge. If nuisance tripping is occurring, the first step is to check all of the connections in the circuit to make sure they are tight. The next step is to try to identify any appliances that may be causing the problem. If the problem persists, it may be necessary to call an electrician. Another common issue is a breaker that won't reset. If a breaker trips and won't reset, it is likely that there is a short circuit or an overload in the circuit. The first step is to turn off all of the appliances and lights in the circuit. Then try to reset the breaker. If the breaker still won't reset, there is likely a short circuit. The short circuit will need to be located and repaired before the breaker can be reset. Another issue is a breaker that is hot to the touch. If a breaker is hot to the touch, it is likely that it is overloaded. The first step is to reduce the load on the circuit by turning off some of the appliances and lights. If the breaker is still hot to the touch, it is necessary to call an electrician. Another issue is a breaker that is making a buzzing sound. If a breaker is making a buzzing sound, it is likely that it is failing. The breaker will need to be replaced as soon as possible. It is important to regularly inspect the electrical panel and circuit breakers to make sure that they are in good working order. If any problems are noticed, they should be corrected as soon as possible. Ignoring problems with the electrical panel or circuit breakers can lead to a fire or electrical shock. When working with electricity, it is important to take precautions to protect against electrical shock. Firstly, always turn off the power at the breaker before working on any electrical circuits. Secondly, use insulated tools. Thirdly, wear rubber gloves and shoes. Fourthly, never work on electrical circuits when wet. Fifthly, if unsure about something, call an electrician. Electricity can be dangerous, but by taking precautions, one can protect themselves from electrical shock. Understanding circuit breaker types is crucial for electrical safety and proper circuit protection. Firstly, standard circuit breakers are the most common type, designed to protect against overloads and short circuits. Secondly, ground fault circuit interrupters or GFCI breakers protect against ground faults by detecting imbalances in current flow, commonly used in bathrooms and kitchens. Thirdly, arc fault circuit interrupters or RFSI breakers detect arc faults, which can cause electrical fires, typically installed in bedrooms. Fourthly, dual function breakers combine GFCI and RFSI protection in a single unit, offering comprehensive safety. Fifthly, shunt trip breakers can be remotely tripped, allowing for emergency shutdowns or remote control of circuits. Sixthly, high-ampacity breakers are designed for high-current applications, such as industrial equipment and large appliances. Seventhly, miniature circuit breakers or MCB are compact breakers used in residential and commercial settings for branch circuit protection. Eighthly, molded case circuit breakers or MCCBs are used in industrial and commercial applications for higher current and voltage protection. Ninthly, insulated case circuit breakers or ICBs provide enhanced insulation and are used in high voltage and high current applications. Tenthly, solid-state circuit breakers use electronic components to detect and interrupt faults, offering faster response times and increased reliability. Choosing the right circuit breaker depends on the specific application and electrical requirements, ensuring safety and efficient circuit protection. Furthermore, different applications of circuit breakers exist across various settings. In residential settings, circuit breakers protect lighting circuits, appliance circuits, and outlets from overloads and short circuits. In commercial buildings, circuit breakers safeguard lighting, HVAC systems, and office equipment. In industrial facilities, circuit breakers protect heavy machinery, production lines, and control systems. In data centers, circuit breakers ensure uninterrupted power supply to servers and networking equipment. In renewable energy systems, circuit breakers protect solar panels, wind turbines, and inverters from electrical faults. In transportation systems, circuit breakers safeguard electrical systems in vehicles, trains, and aircraft. In marine applications, circuit breakers protect electrical systems on boats and ships. In healthcare facilities, circuit breakers ensure reliable power for medical equipment and life support systems. In telecommunications infrastructure, circuit breakers protect communication equipment and network servers. In critical infrastructure, such as power plants and water treatment facilities, circuit breakers ensure continuous operation and prevent disruptions. The specific type and rating of circuit breakers used will vary depending on the application's electrical demands and safety requirements. Ensuring proper circuit breaker selection and maintenance is essential for electrical safety and operational reliability. The National Electrical Code, or NEC, provides comprehensive guidelines for the proper selection, installation, and maintenance of circuit breakers. These guidelines are designed to ensure electrical safety and prevent electrical hazards. Some key NEC requirements include: firstly, circuit breakers must be listed and labeled by a recognized testing laboratory, such as UL. Secondly, circuit breakers must be properly sized for the circuit they are protecting. Thirdly, circuit breakers must be installed in a readily accessible location. Fourthly, circuit breakers must be protected from physical damage. Fifthly, circuit breakers must be properly maintained and tested regularly. Sixthly, NEC Table 310.15b16 provides opacity ratings for conductors based on insulation type and temperature rating. Seventhly, NEC Section 240.4b allows for the next higher standard of a current device rating if the conductor ampacity does not correspond to a standard breaker size. Eighthly, NEC Section 210.20 requires overcurrent protection for branch circuits to be size no greater than the ampacity of the circuit conductors. Ninthly, NEC Section 408.36 requires overcurrent protection for panel boards to be sized no greater than the panel board's rating. Tenthly, NEC Article 230 covers service entrance conductors and equipment, including overcurrent protection requirements. Following the NEC guidelines is essential for ensuring electrical safety and compliance with local codes and regulations. Consulting with a qualified electrician is recommended to ensure proper circuit breaker selection, installation, and maintenance. Regularly inspecting and testing circuit breakers is important to identify potential issues and prevent electrical hazards. Firstly, visually inspect circuit breakers for signs of damage, such as cracks, discoloration, or corrosion. Secondly, check for loose connections or damaged wiring around the circuit breaker. Thirdly, test circuit breakers using a circuit breaker tester to verify proper operation. Fourthly, measure the voltage and current at the circuit breaker to ensure it is within the rated limits. Fifthly, perform thermal imaging to identify hotspots or overheating components. Sixthly, keep circuit breakers clean and free from dust, dirt, and debris. Seventhly, replace any circuit breakers that show signs of wear, damage, or malfunction. Eighthly, maintain a record of circuit breaker inspections and testing. Ninthly, train personnel on proper circuit breaker maintenance and troubleshooting procedures. Tenthly, follow manufacturers' recommendations for circuit breaker maintenance and testing. Regular inspection and testing can help prevent circuit breaker failures, reduce the risk of electrical hazards, and ensure the reliable operation of electrical systems.